three-phase electrical systems, understanding neutral current is essential. The formula you presented suggests you're trying to calculate the neutral current based on the phase currents. The neutral current in a three-phase system is indeed the vector sum of the currents in the three phases. It's the current returning to the source via the neutral conductor. In a perfectly balanced three-phase system, where the currents in all three phases are equal in magnitude and have a 120-degree phase displacement, the neutral current theoretically is zero. This is because the currents effectively cancel each other out. However, real-world scenarios often involve unbalanced loads. An unbalanced three-phase system occurs when the currents in the phases are unequal, either in magnitude or phase angle. The greater the imbalance, the larger the neutral current becomes. The neutral current represents the difference in current between the phases, providing a path for the unbalanced current to return to the source. Therefore, when phase currents are not identical, a neutral current will exist. Harmonic loads further complicate the situation. Harmonic currents are non-sinusoidal currents introduced by nonlinear loads, such as electronic devices. These harmonic currents can flow in the neutral conductor, even when the fundamental frequency currents appear balanced. This is because different harmonics have different phase relationships and don't necessarily cancel each other out in the neutral. For example, triplet harmonics, which are odd multiples of the third harmonic, such as the third, 9th, and 15th harmonics, are additive in the neutral conductor in a three-phase four-wire system. This means they don't cancel and can significantly increase the neutral current. The presence of substantial neutral current can lead to several issues. One is overheating of the neutral conductor. Excessive current flow generates heat, which can damage the insulation and potentially cause a fire. Another concern is voltage distortion. Neutral current can cause voltage drops along the neutral conductor, leading to voltage imbalances at the loads and affecting the performance of sensitive equipment. Finally, neutral current contributes to power loss in the system, reducing overall efficiency. To mitigate these issues, careful design practices are necessary. One is to balance the loads across the three phases as evenly as possible to minimize the imbalance and the resulting neutral current. Another is to employ filters to reduce harmonic currents generated by nonlinear loads. These filters can be installed at the source of the harmonic currents or at a central location in the electrical system. Additionally, oversizing the neutral conductor is a common practice to accommodate potential neutral currents and to reduce the risk of overheating. The National Electric Code, or NEC, specifies requirements for neutral conductor sizing in three-phase systems. For example, NEC Section 220.61 provides guidance on calculating the neutral load for household electric ranges and similar cooking appliances, and Table 310.15b16 provides ampacity ratings for conductors. Another key part is in NEC 310.15 cone, which details conditions of use, including considerations for ambient temperature and the number of current-carrying conductors in a raceway or cable, potentially requiring ampacity adjustment factors. Proper grounding and bonding practices are also crucial to minimize neutral to ground voltage and to provide a low impedance path for fault currents, ensuring electrical safety.